My name is Hubarevich. I'm from the Laboratory for Zero Carbon Energy, and today I would like to introduce my recent research on induction heating-assisted synthesis of ceramic materials, from binary carbides to novel max phases. So ceramics are inorganic, non-metallic materials made up of ionic, covalent, or mixed bonds. And we can divide ceramics into two big classes, such as oxide ceramics, shown here, alumina, zirconia, or yttria, and non-oxide ceramics, such as carbides, silicon carbide, boron carbide, nitrides, and borides. Ceramics possess superior properties, such as low density, exceptional resistance to heat, chemicals, plasma, and wear. Therefore, ceramics are indispensable materials for electronics industry, semiconductor processing, aerospace, energy and environmental field, machining, sensors, catalysts, and so on. Manufacturing of ceramics has a lot of steps. It includes synthesis of powders, milling, making slurries, drying, and sintering of powders into bulk ceramics. Each step requires a lot of energy and time. Therefore, it's well known that the ceramic industry is an energy-intensive industry with high carbon dioxide emission. In case of oxide ceramics, recently novel sintering processes such as cold sintering have been proposed to decrease temperature of processing and decrease energy consumption. However, in case of non-oxide ceramics, in many cases, still long hours heat treatment under very high temperatures, higher than 1500 degrees C, is still must for the synthesis and sintering. So here we come to motivation and approach in my research. So my motivation is to contribute to decreasing energy consumption and carbon footprint in manufacturing of non-oxide ceramics. So my purpose is to develop a new, facile, energy-saving, and environmentally friendly method for synthesis and sintering of non-oxide ceramics. Today, I will concentrate on synthesis. And my approach to synthesis is based on two ideas. First idea is to use heat of chemical reactions to decrease outer energy input. So actually, majority of chemical reactions used to synthesize non-oxide ceramics are exothermic. However, despite of that fact, high temperatures and long hours treatment is used. The reason is kinetics of the chemical reactions. But I consider it that if we can control the kinetics of chemical reactions to overcome diffusion kinetic barriers, we can decrease temperature and time necessary for synthesis. Let me introduce my method. So it's induction heating assisted synthesis. And it's based on two techniques, combustion synthesis and induction heating. So combustion synthesis is a well-known method to synthesize high-temperature materials, and this method is based on utilization of highly exothermic chemical reactions. This method is effective, but it has its own drawbacks. We need only highly exothermic reactions. Only highly exothermic reactions can be applied. Moreover, it's very difficult to control the combustion synthesis product. As a result, process is very difficult to control. As a result, it's very difficult to get desired properties of the product, such as purity, particle size, and so on. So to overcome these drawbacks, I propose to apply induction heating technique. Induction heating technique is a well-matured method to heat materials. So the scheme is shown here. Induction heating is based on passing an alternating current through coil, and then electrically conducting object put inside the coil is heated up contactlessly and very fastly. Moreover, with induction heating, we can control heating rates in a very wide range. As a result, through combination of combustion synthesis and induction heating, it's possible to design finely controlled and fast synthesis. How this method works? I will demonstrate three examples of synthesis. First is synthesis of second hardest material in the world, boron carbide. Second is synthesis of novel wide bandgap ternary carbide aluminum silicon carbide. And finally, I will talk about synthesis of machinable ternary carbide ceramics with metallic properties, titanium-3 silicon carbon 2. Okay, let's move to the first example, boron carbide. Boron carbide has superior properties. It's very hard, it has low density, high melting point, and so on. Therefore, this material is widely applied in wear-resistant components and in neutron absorption and shielding materials. Commercially, boron carbide produced by two methods, carbothermic reduction or from elements. But all these methods require temperatures higher than 1500 degrees and long duration of heating. As a result, coarse products are formed. And to process them, we need to ground them to get fine particles. And then it takes a lot of time because boron carbide is very hard. So let's take a look on my synthesis. So induction heating assisted synthesis of boron carbide. As I explained, my synthesis is based on two main ideas. First is exothermic reaction we use. So direct reaction between boron and carbon, as shown here, is exothermic, so it's okay. And second idea is to control the reaction precisely. I used induction heating to preheat, initiate, and control temperature of the reaction. Experimental setup is shown here. It's very simple. And on this graph, I show temperature profile during the reaction. This is temperature and this is time. Please pay attention to the time scale here. It's in seconds. So we preheat our mixture and then ignite with very fast heating rate higher than 1000 degrees per minute and initiate the reaction. And then we post-heat to control properties of the product. As a result, we get powders with particle size in few nanometers, and our powders demonstrated exceptional oxidation resistance. So we can conclude with induction heating assistance, we can synthesize boron carbide in less than 10 minutes. Next, let me explain about synthesis of aluminum silicon carbide. This is a novel material. Its crystal structure is shown here. It has low density, high melting point, high oxidation resistance, wide band gap, and photocatalytic activity. Despite this material is very interesting, research on aluminum silicon carbide is still restricted by the difficulty to synthesize a single phase. Here we proposed our method to use heat of the reaction and induction heating assistance. So the reaction between elements to form aluminum silicon carbide is exothermic, as shown here. And we developed induction heating program, as shown here, consisting of 3 steps. Please take a look on this time scale. Heating program takes only 5 minutes. And as a result, we can get this yellow color product with particle size in few micrometers. So we could synthesize single-phase aluminum silicon carbide powders in just 5 minutes. If you compare it with conventional methods, you will see how fast is our method. And finally, let me explain about synthesis of titanium-3 silicon carbon 2. This titanium-3 silicon carbon 2 belongs to max phases. Max phases are ternary compounds which have properties in between metals and ceramics. So they have merits of both metal and ceramics. Like, for example, this max phase has high electrical conductivity as a metal, and it's machinable. It can be shaped in different forms. Moreover, max phases serve as sources for two-dimensional Maxine materials, which are widely used in various fields. So wide application of max phases is expected. However, this ternary carbide is quite difficult to synthesize in pure form. So we proposed our method to synthesis of titanium-3 silicon carbon 2. First, we control the heat of the reaction. This reaction is highly exothermic. So to control the heat, we add titanium carbide and then get optimal heat. And then we design induction heating program to keep the conditions in optimal range. As a result, with induction heating assistance, high purity titanium-3 silicon carbon 2 powders were successfully synthesized. So let me summarize my talk. Induction heating assisted synthesis of ceramic materials has been developed and successfully applied to synthesis of fine crystalline powders of second hard material in the world B4C, also to a novel ternary carbide aluminum 4 SiC4, and to MaxPhase titanium 3 silicon carbide 2. In all cases, high-quality fine products were obtained with heating time of just 5 to 10 minutes. And currently, I'm looking for novel targets for my research, and also I'm developing sintering techniques based on induction heating assistance. Thank you for your attention.